Welcome to this introduction to the adaptive Neuro-Symbolic network agent, a system inspired by the non-axiomatic reasoning system proposed by Dr. Pei Wang. Differently than NAS, ANSNA is a sensory motor system. It borrows three levels of NAS non-axiomatic logic, that is, Nel 1 for event matching and perception, Nel 7 for temporal inference, and Nel 8 for procedural inference. A key feature of the system is that instead of terms and compound terms, ANSNA uses sparse-distributed representations. Those are long bit vectors with only a few 1-bits. However, a big question is how the system's internal activities should be controlled. Its control mechanism is inspired by Tony Lofthouse' system, Adaptive Logic and Neural Network, or ALAN. The temporal inference and procedural learning mechanisms are taken from OpenNAS. What makes ANSNA special is that it can efficiently process large quantities of sensor information. That's mostly due to its usage of sparse-distributed representations, which modern processors with its larger registers and vector extensions can process quite efficiently. SDRs can encode semantic information, for instance by assigning words to random SDRs. The longer the SDR, the more unlikely it is that 1-bits will overlap. Due to this property, SDRs can encode independent features, like shown in the image. While semantic features are typically encoded in multiple 1-bits, each 1-bit in the SDR can be seen as the presence of a unit of information. Hence, the intersection carries only the information from both component SDRs. If the intersecting bits happen to encode a semantic feature, the feature will also be present in the outcome, or in different words, common features will be exploited, others will be extinguished. With the union operation, implementable by both OR and XOR, on the other hand, all features will be combined, and with a difference operation, all the features that differ can be calculated in one go. All semantics preserving operations just by bitwise operation between two SDRs. How beautiful is this? Additionally, it is possible to encode structure into the SDRs using random permutations, mapping all the 1-bits to new places within the SDR in a deterministic way. The output will be different to the input, but similar inputs will lead to similar outputs, preserving structural similarity. Sequences and arbitrary relations that usually demand a symbolic encoding can be encoded into SDRs this way. Events are how all information enters the system, but they can also be derived sequences. They always contain a SDR and are either a belief or a GOR. Also they have a occurrence time, frequency and confidence value attached to them, similar like NAS. Events drive the formation of new concepts in the system. These are initiated with the event that led to their creation, but will adapt the SDR using conceptual interpolation, which I will explain later. They also track how often they have been matched by an event, because we only want concepts that are used often to survive in the system's memory. Concepts also store predictive links to other concepts. That's how the system can learn what events usually lead to others occurring, and how its operations lead to different outcomes in different circumstances. When matching events to a concept, it makes use of the winner-takes-all principle, in NAS called choice rule. The match value is motivated by asking for the truth value of to what extent the event is a special case of the pattern represented by the concept. The positive evidence for the answer is given by all 1-bits the event and concept SDR has in common. The negative evidence is given by the 1-bit the event SDR has but the concepts STR does not. And the total evidence is now the combination of both. This way, a match frequency value can be structurally established, that is, the positive evidence divided by the total. The confidence is the total normalized to a value from 0 to 1, never reaching 1. Given that we know that the event represents its STR with a certain truth value, and that the event STR matched to the concept with a certain truth value, using deduction, we can now determine how much the event matched the concept. Whenever a concept is the best match for an event, the concept STR gets adjusted. This is done in the same way as in Benty-Canerva's sparse-distributed memory system. Basically, a counter is kept for each bit position of the concept STR. For each bit index, if the event has a 1 bit in its STR at this location, the counter for that index gets increased, else decreased. Does it rise above a threshold at the index, the bit will be set in the concept STR at the same index, else reset. This simple principle allows the system to identify a common pattern in input, for instance to build a concept for a perfect circle, even though it has never been observed perfectly, like shown in the picture. But there is more. By event matching activated concepts can predict what will happen next, while being able to take own actions into account. They do that using predictive links, which link concepts together using their STR. Additionally, they can have operations attached to them, which is like a part of the precondition necessary for the outcome to happen, but which can be triggered by the system itself whenever it desires, meaning the outcome concept has a corresponding recent core event with sufficient desire value. Predictive links are also responsible for subcore derivation by generating core specs. Basically, if the core event enters, the related concept chooses the incoming link that most likely leads to itself happening and executes the attached operation. If however the link isn't strong or true enough, or the precondition didn't happen recently enough, it will send a subcore spec to the concept of each incoming link, meaning the system will try to get the preconditions necessary to achieve the outcome done next. All the activity of the system follows the following patterns, which in NAS are called inference rules. Since ANSNA is more like a neural network, it's better to think of them as schemas of adaptation that happen within the system. For instance, revision and choice describe a Hebbian-like growth process of predictive links between active concepts and the accumulation of event truth value in concepts, which can be seen as a form of action potential. Intersection and deduction describes the generation of derived events for building sequences, predicting outcomes, and deriving subcores. The big picture can be seen here. We got the event buffer, in which input events and derived events stream into, and are priorized according to their truth value and currentness, kicking out weak candidates by enforcing a fixed capacity. Then there is a memory storing concepts, ranked according to their usefulness, currently organized into layers of abstraction. The concepts form predictive links to each other, and are able to predict each other's activeness while invoking operations, or to send subcore spikes to others over the event buffer. Overall, the system is an adaptive core-driven decision maker, entirely driven by event activity. It is adaptive since it learns invariance in input and learns to predict outcomes. It is neuro-symbolic since it uses a sparse-distributed representation in which one can encode literally anything. It is some kind of network, since concepts are linked to others with predictive links and send signals to each other. It is an agent because it can make core-dependent decisions, hence ANSNA, ANSNA. The system has been presented at the Conference for Artificial General Intelligence in 2019 and has been published accordingly. Now I will show you some demos. There's a stable C implementation. First, there are two versions of Pong, which the system learns to play pretty well in a very short time. The OpenNAS multi-step decision-making experiments in the link you can follow have all been successfully replicated using ANSNA. Additionally, there is a new experiment for learning hierarchical feature compositions. So far, MNIST is used, on which the system is trained on in an unsupervised way, without labels. While the system was not tuned for vision, its memory has some for the task beneficial properties. ANSNA's current memory is organized into layers, where it passes events as well as unfulfilled cores up. Higher levels have less capacity, so entries get matched more often and need to perform conceptual interpolation more often, leaving the system with more abstract features at higher levels. This alone isn't sufficient to learn proper visual object compositions or to be able to form all kinds of abstract AGI-relevant concepts from sensory information, but it's a start.